All right, so we are beginning part 2 of the speed and velocity lesson. We just finished the problem with the coach pacing back and forth, and now we're going to move on to figuring out how do we glean velocity and speed from a position versus time graph. Now, we've already briefly talked about this, so it might be a little bit of review, but we're going to get some good practice with this skill here. So remember, when we're looking at a position versus time graph, our slope is our rise over our run. Now your rise is how much you change on the vertical axis. So I'm going to color code here. My rise is how much I change on the vertical axis. Well, if my vertical axis is position, then my rise is change in position, commonly called displacement. My run is how much I change horizontally on the graph. So in this case, since time is on my horizontal axis, my run is delta t. In other words, just change in time, or AKA a time interval. I like to use the word or the phrase time interval to denote the difference between a change in time versus a moment in time or an instant in time. That being said, my displacement over time interval is the same thing as my average velocity. So what does this mean? My slope, I'll use a good color that I haven't used yet, purple. My slope of a position versus time graph is the same thing as my average velocity. So let's say we've been presented with this graph and we were asked to find the velocity of the object graphed below. All we'd have to do to find the velocity is to find the slope. So my slope is just going to be my rise over my run between 2 points. Now there have been 2 points selected already for you on this graph. The rise between these 2 points is down 2 meters. Down is the same thing as negative 2 meters or minus 2 meters. My run is how far to the right I went, and between these 2 points I went right 3 tick marks, which represents 3 seconds. So what does this fraction mean? Well, in everyday real-world terms, what this fraction is telling me is that every 3 seconds, the object was displaced negative 2 meters. Hopefully that kind of creates a visual on a number line for you, that every 3 seconds, this object is moving to the left 2 meters. Now, I could simplify this so that I wasn't looking at every 3 seconds. For example, when I plug this in my calculator, I end up getting a value of negative 0.67 meters per second. But what does this value mean in everyday real-world terms? This value means that every second the object is displaced negative 0.67 meters. In other words, if I was looking at a number line, every second my object would move to the left 0.67 meters. Now, let's say I wanted to find the speed of this object graphed above. Luckily, finding the speed is pretty straightforward because for this graph, my distance equals my displacement. How do I know that? Well, I can tell that this object only went in one direction. It didn't turn around at any point in time in its travel. So the length of its path is actually going to be the same value as its change in position. So my average speed is going to have the same magnitude as my average velocity, 0.67 meters per second. The only difference is that there's no direction associated with this. So I don't have to say negative 0.67 meters per second. I can say just regular 0.67 meters per second since it's a scalar quantity. Let's try one more problem together. Now we've got a graph that shows a line going linearly and then changing to a horizontal flat line, indicating there's a change in motion for this object during its time of travel. Let's try to find the speed and velocity of this object during 2 time intervals. The first time interval we're going to focus on is from 0 seconds to 5 seconds, and the second time interval is from 5 seconds to 10 seconds. So I'm going to have 2 different sets of calculations, which I've already kind of set up and color-coded here. For my interval from 0 to 5 seconds, I'll do those calculations for the blue velocity and speed values that I have written here, and then for my interval from 5 to 10 seconds, I'll do that for my yellow. So from 0 to 5 seconds, if I wanted to find my velocity, I just need to find the slope of my line. So my rise over my run. My rise is up 25 meters. My run is over 5 seconds. Oops, maybe revealed too much. There we go. When I simplify this fraction, I end up getting an average velocity of 5 meters per second. Now, since this object didn't change its motion during the interval, my distance traveled is the same thing as my speed. So my velocity and my speed are going to have the same magnitude. So speed will also be 5 meters per second. Now, if I look at my interval from 5 to 10 seconds, my slope is going to be different now because my points don't actually have a rise. In fact, there is no change in position from 5 to 10 seconds. In other words, there's 0 displacement. So even though my run is 5 seconds, my rise is 0, and 0 divided by any value gets me 0. Now, I also revealed my speed, couldn't help it. So if my average velocity is 0, my average speed is 0 as well, since there was no backtracking that happened during this time. So my distance and my displacement are the same from this 5 to 10 second interval. Now this next one I'd like for you to try without me. Go ahead and pause the video and unpause when you're ready to check your answer. All right, I'm assuming if you're listening to this, you're ready to check your answer to this example. We're going to try to find the speed and velocity of this object during 2 time intervals, from 20 seconds to 40 seconds, and then from 40 seconds to 5 seconds. And I've already kind of set it up for you. So from 20 seconds to 40 seconds, my rise is negative 80 meters, and my run is 20 seconds. So my average velocity is negative 4 meters per second. Now my speed is going to end up having the same magnitude since there was no backtracking that occurred. It's just going to be absent of direction. So my speed during this interval is 4 meters per second. Now to figure out what my average velocity and speed are from 40 to 55 seconds. My rise is 40 meters, positive 40 meters because it's up 40. My run is 25 seconds. When I simplify this, I get an average velocity of positive 1.6 meters per second. And my average speed is going to have the same magnitude. So it will also be 1.6 meters per second. Now let's look at one last problem together. This one is also a try, but there are many, many parts to it. So feel free to maybe attempt some parts and unpause the video to check as you go, or go through all 5 of them, 6 of them, and then unpause when you're ready to check them all. All right, I'm going to assume if you're listening to this, you're ready to check some, if not all, of your answers to this problem. So the position versus time graph below represents the motion of South's basketball coach during the last 16 seconds of the overtime during this past weekend's game. So it seems like he was going back and forth a lot and standing still in some instances. So let's get started. So letter A says determine the total distance walked by the coach during these 16 seconds. So I'm going to scroll down to show my work here. So for the first interval, I will highlight that here. My total distance traveled is from 0 to 8 meters, meaning my position, I guess I should reveal, or my distance was 8 meters. For the second interval, from 4 to, I think that's 6, from 4 to 6 seconds, his position stays constant at 8 meters. So he doesn't move, therefore he doesn't travel any distance. So I'm not going to include that. From 6 to 8 seconds, he goes from a position of 8 to 4, meaning he traveled 4 meters. From 8 seconds to 10 seconds, his position stays the same at 4 meters, so there was no distance traveled during that time. But then from 10 seconds to 14 seconds, 14 seconds, he goes from position 4 to position 8, meaning he traveled again another 4 meters. And then at the last moments of the game, from 14 seconds to 16 seconds, he traveled from 8 meters to 0 meters, meaning he traveled a distance of 8 meters. So when I add all of these distances up together, I end up getting a total distance of 24 meters. Now let's look at letter B. Determine the resulting displacement of the coach during these 16 seconds. Well, my displacement is my total change in position. And initially, he started at position 0. And finally, he ended at position 0. So his displacement is 0 meters. He didn't move his position from beginning to end. Letter C says, determine the displacement of the coach after 12 seconds. So in order to do this, I've got to figure out where the coach was at 12 seconds and where he was at 16 seconds to compare beginning to end. So at 12 seconds, I'm going to estimate this. It looks like he was at 6 meters. Is that accurate? Yep, he was at 6 meters. And then after 12 seconds, it looks like, where did he go? Determining after 12 seconds, he was here, but that doesn't matter. I really I care about where he was here finally, right? Yeah, that's correct. So at 12 seconds, he was at 6 meters. At 16 seconds, he was at 0 meters. So he was displaced a total of -6 meters after 12 seconds. Now for letter D. At what time did the coach have the greatest displacement from his starting position? So there actually were a couple of times that this happened. His greatest displacement was when he was at 8 meters. So at any times that he was at 8 meters, I need to record that. So at 4 seconds, he displaced himself the most. At 6 seconds, he didn't actually get displaced any further. He actually stayed the same. So from 4 to 6 seconds, his displacement was 0. So I'm not going to include 6 seconds in this because his displacement from 4 to 6 seconds was 0. But then, well, I guess I could include it. But I'm not going to. No, I'm not going to. It's not necessary. I feel like that's kind of redundant. The only other place that he was at 8 meters was right here at 14. Right here at 14 seconds. So that's the only other time that I feel like I need to include. 14 seconds. Did I count that right? Yes, I did. You can include 6 seconds. Now that I think about it, I guess it's valuable to include 6 seconds because he was at 8 meters. I think I didn't include it originally because he didn't move there after 4 seconds. He just stayed there. But it is true. He was there. He was there at 8 meters. But then he was there at 5 seconds too. So maybe I think I'd feel more comfortable saying from 4 to 6 seconds during that interval. Instead of at 4 seconds, I'd say from 4 to 6 seconds and at 14 seconds. That's the most accurate way to respond to this. At what time did he have the greatest displacement? Yep, from 4 to 6 seconds in this interval. And then at this moment here at 14 seconds. That's the best way we could respond to this. All right, letter E. What was the fastest speed which the coach walked during any of the time intervals from the 16 seconds? Oh, geez. Okay, so I've got to remember that speed is my distance divided by my time. So I'm going to be looking at all my different highlighted regions, and I'm going to be looking for the region that has the greatest distance in the shortest amount of time. In other words, I'm probably going to want to find my region that has the steepest slope. My steepest slope is going to have my greatest velocity, which is going to have my greatest speed. So I can see right away that the pink and the orange lines have my greatest distances, but my pink line is over an interval of 4 seconds, whereas my orange line is over an interval of 2 seconds. In other words, my orange line is steeper, whereas my pink line is less steep, meaning that my slope for my orange line is going to be greater than it is for my pink line. So from 14 to 16 seconds, I had the greatest speed. Now my iPad's not wanting to respond. There we go. So from 14 to 16 seconds, my displacement or my rise was down 8 meters and my run was over 2 seconds. So my speed is going to be 8 meters over 2 seconds, which reduces to 4 meters per second. Now my last question is, what was the average speed of the coach for these 16 seconds? Now to find my average speed, that means I'm going to want to take my total distance for the entire graph divided by my total time for the entire graph, instead of looking at the colored segments that I highlighted. So my total distance is going to be quite large. If I add up the total distance, I end up getting 24 meters. And if I divide this by the total time of 16 seconds, I end up getting a reduced fraction of 3 meters for every 2 seconds. Or in other words, 1.5 meters per second. All right, so that concludes our last try for this problem, or for these notes. Remember, by the end of this lesson, your goal was to be able to differentiate between speed and velocity. So if there's any confusion on what the difference is between speed and velocity, make sure to get this resolved with me in class before moving on to the next task.